All right, so assuming you have no knowledge of machine learning, how would you program a computer to recognize a picture of a handwritten digit? And again, it's just literally an array of pixel values. So how can we do it? Well, one of the simplest ideas, we have a data set for this also. So we have 60,000 of these images and their labels. This corresponds to a matrix of 60,000 entries by 784 columns, where the rows are examples and the columns are pixels. And then we have 60,000 labels, which would be just integers from 0 to 9. So we want to be able to, from a picture of an image X, predict a value, which is what digit it actually is, Y. So here's a simple idea. For each image, we can find the most similar one and guess that as the label. And it's pretty simple. This is like pseudocode. And literally, this would be just going through every single image in that matrix of 60,000 examples and predicting for any given new example the label of the one that has the smallest inverse distance, which is similarity. So similarity is a very vague concept. And the easiest way we can think of an idea like how similar two things are, or just literally how similar the pixel values are, which would be corresponding to the inverse of the distance. And this works actually pretty well. It's called KNearestNeighbors, and we're using a k value of 1, and this gets you about 95% accuracy. Now, for reference, doing handwritten OCR, you need to get about 99.5% accuracy to be considered commercially viable, so we still got a long way to go. But the main example here is just to say, hey, we can do machine learning, it's not that hard. You can literally do there isn't really learning going on here, this is literally copying and search, but it's something. So, what about going another level? This similarity based on like pixel values is probably not all that great, actually. What if we could write some functions to calculate specific features or computations on the input to get more at the problem? So if, like, for instance, if we have one closed loop and no vertical strokes, we could return a 0. If we have one vertical stroke and the width is kind of tiny, so this is a 28 by 28 image, and if it's less than 10, we could predict a 1. And this is like kind of like a jokey way of doing it, but like you could imagine just playing around writing something like this. And so this is kind of getting at a problem in machine learning typically called feature engineering. It's how to go from your raw data to something more interpretable and more relevant to solving the problem at hand. And the only problem here is we're using hard-coded rules right now, which are really brittle, and like how do you recognize a 1 that's actually got a bottom stroke? That's going to be wide, that's not going to work in this sense. So it's not really obvious or clear how to write these rules ourselves. So this is where machine learning comes in as like kind of a framework. We have a set of inputs, which would be handwritten digits in this case, and then we have, for instance, a black box model that we want to do computation in, and somehow map those inputs to the desired output, which would be, hey, this is an 8. So here's an example of one of those models. It's probably the most complex one I've ever seen, and it came out last month from Google, and it's currently the state-of-the-art at visual object recognition. I think that has 120 different computation boxes and like 28 layers. It's pretty scary. We're going to start a little simpler, which is we're going to take in an input, like an integer, and our computation is going to be, we're going to multiply it by some value, and we're going to get an output. So we can guess from this that we need to multiply it by 4 from this one example. All right, so now we're going to introduce Theano and how we can actually write and code things to do this for us. So we have our imports. Usually you import Theano, and then you import Theano.tensor as T. Tensor is the section of Theano that actually deals with operations on data in Theano. And it's the equivalent, if you've done any numeric Python, it's basically the equivalent of the NumPy library. So Theano is a symbolic library, which means the inputs are instantiated without being directly tied to data, and it's basically a way of typing it and having Theano be able to compile things. All it means is we basically have to declare, here's the kind of data you're going to be operating on, and define Python functions and operations on that data. And then, so we're initializing 2 scalar values, which would be equivalent to integers. Just naked values, nothing else around them. So this is our model, y equals a times b. And then, because this is all symbolic, at some point we need to actually compile it in Theano to an actual accessible Python function to have it operate on actual data examples. And so we do that via the Theano.function interface, and we declare our inputs being these two symbolic variables a and b, and our output being the desired multiplication value y. And then now, when we put in actual values, for instance here, what Theano is doing internally is basically saying, oh, I've got to substitute in 1 and 2 for A and B, and then compute this for you. And the nice thing is Theano.function can compile to semi-arbitrary backends. So right now, this is, depending on how you have Theano configured, this can be running on a CPU or a GPU. And the really important thing is GPUs are very necessary in this space oftentimes, because otherwise these models are very large and very complex, and they just perform too slow on the CPU. So just last week, we ran a model that took about a week on a GPU, which if the equivalent model was run on a CPU, without a cluster, it would have been somewhere on the order of like 2/3 of a year. So it's just not tractable in many ways. And a GPU basically gets you a cluster in a single computer. So it's really important. And the nice thing is that's all abstracted away from us. This Theano.function, if we had set an environment variable to compile to the GPU, would run on a GPU, would run on a CPU. It doesn't really matter right now because we're just doing multiplication of scalars, but here we go. So we have usage, and it works as we'd expect. All right, so here's our trivial example. Now how do we take this and make it into a model that can actually be learnable? So there's a few things we've got to do. I just add NumPy as an import. This is the numeric Python package. It just lets us operate on scalars, vectors, matrices, anything you want to do data-wise. So we're going to generate some data examples. So we're just making a linear space from -1 to 1. And we're saying our underlying truth is the line 2x. And we're going to add some random noise just to make the problem a little more interesting. We've got the same x as input, y as output, scalar initializations. And we've now made a little function to say our model takes in x, multiplies it by y. And then we have to instantiate the model parameters. So what we use for this is the Theano.shared interface. And Theano.shared is the way to have hybrid variables. So x and y being scalars are purely symbolic variables. However, this w that we want as our weight, the multiplication weight, needs to be something we learn. So it's this weird mix where on the one hand it has to have a real value associated, on the other one it still needs to work in our Theano symbolic graph. And that's what Theano.shared is for. It's for hybrid variables. And generally, all you can think of this being, if you're having a parameter of a model, you put in a shared variable. And then we've got our output of our model. And now we need to decide how to actually make this model learn. So the way this is typically done in machine learning is via something called a cost function. And this is basically some metric to tell the model, hey, this is what you're trying to accomplish. And in this case, we're saying it is the mean squared error. So the difference, the squares are the differences of our predictions, y, from our model, versus the actual desired outputs, capital Y. Sorry about variable names. Okay, so how do we actually get a thing to know how to change our model? Well, we can use Theano is typically used for gradient-based learning, and this essentially, you can think of it as a learning signal for each parameter. So what's really nice is because everything's symbolic in Theano, it can take care of a lot of the complex math to get these gradient parameters oftentimes for us. And so we just plug in our cost function, and we just want to know how to change w with respect to that cost, the cost function with respect to our parameter w. And then the way we tell it to actually change that value is via an updates, which is a list of lists format in Theano, which is basically saying, hey, we've got our variable w, and at the next time step, we want to make w minus the gradient times 0.01. So we're doing what's called gradient descent. So we get our gradient and we're moving down it, and we're modifying how quickly we follow that gradient based on a scalar variable called learning rate, usually. And this just is helping with stability. You could imagine if you initialized a model poorly and you got too large gradients coming out of your model, it could just explode, for instance. So this is something we'll come back to, smarter ways of doing this. Then we instantiate the training function, which has inputs x and y. Again, we're just defining the mapping, how to plug actual data values that'll come into our symbolic graph. And output, which is the cost on those examples. And then we're telling it, hey, every time you run this, you need to run that updates function. And then we want to this final thing just basically allows us to ignore some of the typing issues with Theano on whether you're running it on a CPU or a GPU, because on a GPU you can only use float 32 or single precision floating values, and on a CPU you typically use 64, and generally we just don't want to deal with that, so we're going the Python way and just saying, hey, do your type conversions as you want. So finally, we can iterate through the data. In this case, we have 101 examples, And we can iterate through it 100 times, and for each example of input-output pairs, back in that data in model black box output format, we can just train the function. All right, sorry for a lot of talking. Now let's just see this actually work. So here's a nice GIF of Theano running that same code and learning our function and predicting that the weight is 2. Again, we initialized it to 2 times the x. And then you can just see the random Gaussian noise. And you can see as we go on that it's minimizing our cost function. And that's basically the mean of the squared errors of each data example. So let's get a little bit more towards what we actually want to solve, which is, again, recognizing handwritten digits. And the way we're going to do that is via a model called Logistic Regression. And so what Logistic Regression does, it takes in a data example, for instance, an 8, and then we're going to move towards a matrix framework. So whereas before our computations were on scalar values, we're just going to bump it up a magnitude and work with matrices, because that's what you work with. And that is represented as matrix multiplication instead of scalar multiplication, which is via the dot product. And then, so we're going to take our raw inputs, we're going to multiply them by a weight matrix, and that's going to be, you can think of that as a way of projecting our input examples based on each possible class. So we have a 0, 1, 2, etc. through to 9. And then we're going to look at how well any given example corresponds to that weight matrix. And then finally, we have a function on top of that called softmax, which is basically a way of taking the outputs of those responses on our weight matrix and normalizing that to be a probability distribution. So because we are trying to predict which digit it is, it naturally follows that we must be modeling our confidences as a probability distribution over our outputs given a specific input. So you can see in this example that, like, given that 8, there's like a slight chance it could be a 0, maybe because there's a lot of overlap in the top and bottom. You know, a 3, kind of, you can see an 8 being a 3 if you cut off 2 sections over on the left side. And then, you know, big confidence on 8. So the way we'd actually predict with this model is by taking the index or the label that has the maximum response through this function. All right, so now we're going to put this back into Theano's framework. We can do that via, we're going to need to initialize a few helper functions at this point. So what floatx does is that takes care of conversions to the standard operating format of Theano, which would be float32 or float64, and it just dynamically does that based on how you configure Theano. And then we also want to initialize our weights now. So the question is, we're trying to learn these parameters, but how do we decide to start them out? And the way we can do this is by just initializing them to a small random Gaussian distribution. And then our model now is the softmax of the dot product of the inputs with respect to the weights, which is, again, basically just the same as A times B, just we've stepped it up a level. So we're going to load in data matrices, train X, test X, train Y, test Y. This is in the load.py file in the tutorial code. Don't really need to worry about it. I mean, it's just a bunch of loading code, but basically train X is a 60,000 by 784 matrix. Because we have a 28 by 28 image, when we flatten that guy out, that becomes a 784 vector. And we have our testing, which is 10,000 testing examples. We have our training, which is, we've converted into what's called a one-hot format, which is nice for this when we're trying to predict a distribution. All we've done is we've taken those labels 0, 1, 2, 3, 4 and turned them into a 10-dimensional vector and said the one that you wanted to predict is 1 and all the others are 0. So now that we've got that, we've changed our types to be floating matrices, and we now have our P of Y given X, so our probability of the labels given the input, which is what our black box model is trying to do. And then we have our predictions, which would be equivalent to the maximum, the argmax of the probabilities over the first axis. So now we have a different cost function. And Theano is nice in that it comes with a lot of these things for you. And categorical cross entropy is basically a way of thinking, in this case, when we have 0s to 1s, and we're forcing our outputs to sum to 1 and be a probability distribution. It's basically telling it to maximize the value that is actually there and minimize the other values. It's actually just telling it to maximize the value that is the correct class for any given example, and because we're predicting a probability distribution, that corresponds to minimizing the others. So we have the same gradient, the same update rule. The only thing we've changed is we've added in a prediction function. So whereas before we had this train function, which would basically just output how well the model was doing on a given example output pair, and then also call this updates function to actually update your parameters for you. We now have a predict function, which allows us to get actual outputs out of the model. And then we've got our little for loop at the end, which is just going to iterate through the data 100 times, and is going to be generating indices through our data set. So we're going to talk about this a little more in a minute, but essentially, if you have a large data set, say 60,000 examples, there's a lot of redundancy. There's a lot of zeros that look really similar to other zeros in that data set, and you don't really need to get your gradient or learning signal estimate on the entire data set. That's computationally inefficient, so you can use a much smaller subsample. So in this case, we use 128 examples in each one, and these start, and I could have done this much cleaner, sorry about that. It's just iterating through, it's slicing through our training matrix, and computing from start to end, and training on it. And then finally, we get outputs, which are just the index we're on, and the accuracy, in this case, on the test. So what does this model actually learn? Sorry for all the details again. Well, here we can actually see what those weight matrices look like. So it has 10 of these, for the 10 trying to map the input to 10 possible outputs, you know, being how 0 it is, how 9 is it, how 8 is it. And we can see that it's pretty much learned something along the lines of a template model. So our 0, that looks like a 0, our 1 looks like a 0. The way to interpret these is bright positive values, like whiteness, would be positive values in that weight matrix, and dark values would be negative ones. And so there's an interesting thing here, though, if we note. These are very fat, very wide, and that's because we have a problem, which is every digit has flexibility. A template matching model actually isn't going to work that well because you can have a skinny 0 or a fat 0. And right now, this model, when it only has these 10 things to compare the input to, is kind of forced to do its best to like deal with slightly slanted x's and really fat or differentiating the zeros. And you know, that's kind of what it looks like. And some of these guys, the more difficult ones like 8 and 9, there's not really much there. So how does this model actually do? So its actual accuracy is 92.5%. This is actually a step down from that really simple idea we had before, which is KNearestNeighbors. And the reason why is because it's very unreasonable to expect our model with only 10 parameters, effectively, to be able to learn a successful mapping from an image to an output in this case. There's much more complexity to the data set than this model can effectively capture. And as a result, it can't do that well. So now we're going to move to neural nets. And this is where it can get a little more interesting. So what we're going to do is, instead of having this model that just takes in the input and basically through one matrix multiply maps it directly to the output, we're going to give it an intermediate layer to let it implement its own functionality, to try and learn how to extract its own features in a sense. So the way we typically do this is with the same matrix multiply, we then put an activation function on it, which is a nonlinearity, because otherwise a series of linearities can just be decomposed as linearities. You don't get anything from stacking a bunch of linear functions on top of each other because they're still linear functions. And that's what a nonlinearity like the sigmoid function does. So all we've done is we put another layer in the middle. It's the same softmax classification output. And this is what an old neural network looks like. In terms of changes, the only thing we've done is we've taken those initial like gradient calculations here, and since now we have a weight matrix which maps from the input to the hidden representation, and a weight matrix which maps from the hidden representation to the output, we can't just do that one line thing where we just tell it, hey, you need to update W, because we have two W's now. So we're just going to move that into a function called SGD, stochastic gradient descent. And what this guy's going to do is it's going to compute the gradients with respect to a list of parameters. So basically, since our model has two parameters to learn, we're just going to give it a list of those parameters. And it's going to go through each parameter and the gradient it calculated for each of those parameters. And we're defining that same updates rule as before, which takes in a parameter and updates it by p minus g times learning rate. So, sorry about that. So, now to explain a little more effectively what's actually going on here, we can see this as an example on a trivial data set. So this is called the 2D Moons data set. It's courtesy of a Python package called scikit-learn. Basically, we just have two wrapping classes of data. 0 would be red, 1 would be blue. We're trying to learn the model that can find the best line. That's what logistic regression can do, to separate these two data points. And as a result, we have two parameters, which would be the weight of that line effectively on the x-axis and the y-axis. And this is a way of seeing our cost, essentially our cost function. So the star in the middle is the correct minima that's trying to be found by changing the parameter, the two w's from like -2 all the way to -5, or from 2 to -5. And SGD is an algorithm that basically at every time step or every sample of the gradient is going to be descending perpendicular to this cost surface. There's a lot of different other models that we're going to get to that help try to speed this process up. And one of the important things to note is that SGD, as you get into the flatter, later stages of learning, really slows down because you just have that fixed learning rate and your gradients get smaller as you've corrected a lot of the big early error. This plot down here is showing you the training accuracy, or the test accuracy, I don't remember which, it doesn't really matter for this case, of these models as they learn over time. So we can see that SGD actually does way worse than these other methods, which we'll be getting to. But now you kind of have a sense for what SGD is doing. Everyone good with that? All right, cool. So now we're going to move from logistic regression to a neural net. And that's really simple with Theano. We just put in a line that calculates that same hidden state that I had on the previous slides before. And we just attach it, so we compute our hidden state as the multiplication of the input with our weight matrix of the hidden values. And then we compute the P of y given x, the same softmax thing before. So we added in one little extra line to let it have a bit more flexibility to it. So real quickly, the sigmoid function, which we're using here, it's a way of mapping arbitrary scale values from these matrix multiplies onto essentially a probability, just a probability. So for each of these hidden units, we're initializing these weight matrices to be 784, this is the length of the input, by 625. So we have 625 of these units trying to compute values. And we're going to map those 625 units back down to those 10 outputs. So we kind of blow the problem up and then bring it back down again. And what this allows us to do is have much more flexibility. So we initialize the weight matrices. We've just changed it to say we've got this list of parameters and we're going to update it via stochastic gradient descent. So now we can actually see what this model does. So if we give it a little while, it's going to cycle through. And you can see that early on, once there's that big sharpness, and this is what a visualization of what those units are looking for. And it's kind of weird. I don't really see much in the form of actual digits in here. And the reason why is because this is a traditional neural network, and because we have all of these hidden units, and the way that we're currently calculating our learning function, all of these hidden units kind of act together, and they're all being jointly optimized, and so they effectively, one here can explain and fix some of the errors of this guy here. You know, it doesn't look that good actually. There's not really that good of a result here. But we can see maybe a tiny bit of structure if we really want to prod at it. You can see that maybe this guy is effectively detecting the absence of a stroke at that location. You can kind of get that interpretation of everything. But there's nothing too clear. The other thing we can note is we can look at, given two example inputs over the course of time, this is a visualization of how those units activate. And blue would be 0 in this sense, and red would be 1. So these are those two hidden matrices for two examples. And it doesn't really change all that much, actually. When you look at it, there's not really too much going on here. And it's very confusing. There's no real way to interpret what it's doing. Luckily, though, this model is still much better than the previous two models, and we have a test accuracy of 98.4%. So this is what an old neural net does. And it's okay, it's not great. If you know another machine learning model, a RBF, support vector machine, can actually beat this and get 98.6%. Takes a lot longer to train, but there's nothing really too exciting about this. So this is kind of to understand where neural nets come from and why a lot of the hype and recent talks about deep learning come from, and where much more of the modern success comes from. So how do we take this model and change it into a model that does much better and is one of the reasons why we see all of our success today in this field? So there's really only two main contributions. One is we changed our hidden activation function to, instead of being that sigmoid function, which would be this guy here, we've changed it to be this guy here. And this is a rectifier. And what a rectifier does is if the input to the unit is below 0, it just doesn't do anything. If the input's above 0, it does something. And the important thing about this is because your gradients are being calculated, they depend on the derivatives of your activation function. And this guy doesn't really have one, it's just one. So it's nice and clean, and this helps make that learning signal that we rely on via calculating the gradients of parameters with respect to our cost function. It makes it much cleaner, and we'll see how much this helps in a little bit. The other important thing to do is, because these are very complex models, you know, they have these 625 hidden units that can compute whatever they want, and then it can take that, they can overfit a ton. So that model before that got 98.4% with a standard old neural net actually has 100% on the test, on the training data set. So what we do is we add noise or some sort of learned augmentation or some sort of hard-coded augmentation. Hard-coded augmentations would be, for instance, shifting this digit left 1 pixel or right 1 pixel and basically saying, hey, look, it's still a 1. It doesn't matter how you move it left or right in your image. And it's surprising, but that's actually a really important thing, because right now we're effectively flattening these inputs. So you can imagine translating this digit over 1 pixel, and you actually get completely different input dimensions activating because of that single operation. And that's very difficult to learn, and as a result, manual augmentation can help there. But there's a really nice simple form, which is just something called dropout, which is a form of noise. And we'll be getting to how it helps in a minute. The other thing there's actually 3 things, not 2 things here. We give it another hidden layer. So instead of having that 1 hidden unit layer, we now have 2, which gives it even more flexibility, which again, before we already knew that wasn't actually a good thing, because with 1 hidden layer, we already overfit completely on the training data. So I'll be getting back to what 2 hidden layers does in this case, and it's kind of puzzling because you'd expect your model to just overfit more because you gave it double the parameters. All right, so how do we change a standard old neural net that's kind of humdrum into one that's actually decent? So we're going to do a few things here. One, we're going to move in our rectifier function as our activation. That's this guy. 2, we're going to move to a numerically stable softmax. This is just a little bit of detail, but the way Theano does it by default can actually explode. Because you've got an exponentiation in the summation for a softmax unit, you get big values in the EXP and it just goes infinity, and your model all of a sudden diverges because you just had an infinity and you just calculated a gradient with infinity respect to all your parameters, and then all of a sudden all your parameters are not numbers. And that's really annoying, and it happens a lot. So this guy is just like kind of a copy-paste kind of thing. You run into numerical stability issues sometimes. Theano tries to solve these in many ways, but in this case, I still see issues with it. So this is just this is the softmax function, actually. It exponentiates all the values, and it divides by the sum of it, and that allows you to compute that probability normalization. Now we're going to move to something beyond that HTE variable. So this is going to help us learn these deeper networks better and help us learn them quicker. And what this is effectively doing is we're saying, instead of always just updating by the gradient times some fixed amount, we're going to now update by, we're going to scale the gradients. So in the same case as before, where we had this fast initial learning in these areas of high cost function issues and high steepness, once you get more towards optimizing the last little bit, things slow down a lot for HTEs. And the way we can get around that is kind of scaling the gradients. So what we do is we make an accumulator variable, and we accumulate the norm of the gradient, which would be just the square of it, and we use a running average format. So rho is like a, or R naught, whatever it's called, is like a averager over time. So if you think about it, a value of 0.9, and you take a value like 1 and multiply it by 0.9 over and over again, it's going to be an exponential decay. So this is just a way of computationally efficiently computing a running average of your gradients. And then what we're going to do is we're going to scale it by the norm of the gradients. So whereas before we slowed down a lot in these areas where things got smoother, RMSprop, which is this guy in black, is going to be much more effective at continuing to learn and accelerating in those areas where things are much smoother. And so this helps speed things up, which is important when we just made our network twice as large and therefore it takes twice as long to run. And this is just, there's a lot of techniques. So there's momentum, there's Nesterov accelerated momentum, there's Adagrad, there's Adadelta. They're all about this complexity and they all do different things. A lot of them are, they basically break it into two techniques. One is the concept of accumulating your updates. That is what momentum and Nesterov accelerated momentum do. And they make this much smoother learning trajectory. But you see that they actually like accumulate something along the lines of a velocity term and they end up overshooting. There are newer actually, with the exception of MAG. These newer methods tend to use something along the lines of your online gradient estimates like SGE, but do some sort of acceleration of the gradient by, dividing the gradients or scaling the learning rate. So instead of always using 0.1 as your learning rate, you're going to adaptively change it based on the local conditions. And that's what these newer techniques do. And they're very important to help optimize these deeper neural networks. All right, one more thing, which is we're going to add dropout, which is this way of injecting noise into the structure of our networks. And this helps a lot with overfitting. And the way we do that is we take in a value, a probability, and then we so like if we want to drop half our units, we put in a probability of 0.5, we calculate the retaining probability. This is just the way Logistic did it. So if you had a P of 0.2, you would correspond to keeping 0.8% of those units. And then for all the units where this actually does evaluate to not keep, it just multiplies them by 0. So it's a way of like dropping out on any given computation the contributions of a subset of your hidden units. And what this does is it makes your model need to be much more robust, and it forces those hidden units to compute values that are much, effectively, you can't have a hidden unit rely on another hidden unit doing something, and the noise as well helps with exploration and changing, and we'll see some visualizations of this in a moment. The other minor trick here is because we dropped out half the values, we need to actually divide by effectively the amount. So if we're keeping 0.5 and we dropped out half, we should scale the remaining ones left by 2x. And this is a way of, it's just a housekeeping kind of thing, but we want the activation at any given layer to always be consistent. And these noise techniques can kind of mess with that. And in the case of removing a bunch of things, we equivalently scale up the things that are left over. Now that we've got that, we have our new model, which is this nice 2-layer hidden network, which computes, it just drops out the input for this problem, and then it computes your new initial hidden layer. It then drops out things from that hidden layer representation, computes the second hidden layer, it then drops out things from the second hidden layer, and computes your outputs. So it's not too different. Again, it's just like doubling the number of lines again. And the important things are we have noise injected into our model. We're now using rectifiers, and we have 2 hidden layers, which allows us to do more computation. So what does a modern net learn? Well, there's a few interesting things in comparison to the previous picture. I'm going to let this go through a few more times and quickly bring up the old picture. So we can see from the old picture that it's this kind of weird mess of stuff, and it doesn't really visually correspond to anything intuitive. But if we actually look at what this new guy is doing, what we're actually seeing here are effectively stroke detectors, and in some cases, digit prototypes. So this is effectively a 1 checker. This unit is responding to 1s. These other units are, you could see this being maybe a 6 responder, you could see this being components of an 8 responder, and this is just in that first hidden layer. And more importantly, because we've added in that noise, we see a few more interesting things. One is these things are learning much better. They continuously learn throughout the process, and the noise helps keep learning happening. So if we looked at this compared to the previous one, you'd see that these continue to tweak and adjust as learning goes on much better than previous ones. And then the other interesting thing is, now that we've moved to rectifiers, we can see on the visualizations of the hidden states of the first hidden layer and the second hidden layer that early on, well, this representation is way more sparse. So sparse is a concept that people like in this space a lot, and it basically, we can see that because we're using rectifiers which hard threshold at 0, a lot of our units just aren't turned off. And the kind of heuristic or understanding to have with this is, we know when we're trying to understand a 7 or a 2, that there's only really a few things present at a given time. For a 2, there's this kind of stroke which is the curve of the top. And there's lots of different strokes at the curve of the top of the 2 that could be, and that's why we have a bunch of hidden units to try and compute these things. But for this unit, we could basically describe it as a curve stroke at the top a diagonal stroke in the middle, and a horizontal stroke at the bottom. So theoretically, you could effectively explain this too with only 3 units. And that's what these sparse representations try to help us get towards, is enforcing the fact that for any given example, we only have a few things active at any given time. The other cool thing that's going on here is you can see actually that, you can see as we learn that the representation gets sparser as we go. So early on, you see this quick flash and there's a lot more values present, but as we kind of bake into the later stages of learning, it's gotten much sparser. So it's kind of getting towards that goal we want. The other interesting thing is the learning is much more dynamic with the noise injected into the network compared to the previous version. So if we looked again, I should have moved these two next to each other. This guy pretty much starts, has a rapid flash at the beginning, and just stops. Whereas with our noise-injected network, we're seeing changes all the time. Values are all, hidden units are always changing, things are turning on or shutting off. And these are just the same inputs fed in again and again over the course of training. So that's a lot of talking and a lot of hand-waving justifications of why these things better, but at the end of the day, the accuracy is way better. We're up to 99%, so we've closed the gap to commercial viability by half by using one of these modern things. So we're not there yet though, and that's kind of disappointing. But as a quick aside thing, here's how you can see the difference between a net from 2000 using just straight SGD with sigmoid hidden units and set learning rate versus one of these modern rectifier nets. And you can see that within the first, I think it's the first like 3 iterations to the training data. It's better than the standard net from 2000 at the end of 100 iterations to your training data. So even with just these quick, simple improvements, rectifiers, noise, and 2 hidden layers, we can effectively make the same network 15x faster without using any computational improvements. And that's because we've got 2 hidden layers, so we have more flexibility in our capability of computation, and rectifiers learn much more cleanly because the gradients don't get distributed or shrinking because of derivatives. So let's get a little bit more at what's actually going on and what multiple hidden layers are doing. So this is a visualization technique that takes your inputs and tries to map them down to a low-dimensional space while preserving the structure of the input space. So we have 784 dimensions for these digits, which would be pixel values in any given location, 2, 3, whatever. And this technique called T-SNE is what the name, I believe it's T-SNE, T-Distributed Stochastic Neighbors Embedding. And what it's trying to do is basically say, hey, similar things clump them together, dissimilar things push them apart, and do this in 2D because we can't understand what's actually going on natively in a 784 dimensional space. So this is what the raw input looks like. And if we train the model directly on the raw input, we get about 8.2% error. And the thing that's interesting to note here is, I'm sorry I didn't put up the actual labels of which are which. I'm just going to talk about this cluster of 3 here. These are the 4s, the 9s, and the 7s. And you can kind of think of that as 4s and 9s are actually really similar. So it's not surprising that they actually have some of the most merged. And there's a weird middle ground, which is like a 9 that's got a small curve, or a 7 that follows the same trajectory, because it's just working on raw input space. So let's see what happens as we go through our deep neural network now. First off, there's a huge improvement between just the first input layer and the first layer, which is the input, and the actual first hidden representation. And you can see that things are much better separated. You see much more gaps between our clusters, which are those natural digits. Again, the color codings are just like the 0s, the 1s, the 2s. That's how you can think of these clusters. And there's still confusion in the middle, but it's much more well separated than the input. And this is confirmed again by training a model on this first hidden layer representation, and that one gets about 2.78% error. If we keep going through the structure of our network as we go more and more hidden layers in, we see this trend continue. Each layer, we get a better differentiation, and a model trained on that layer with no ability to change it is much more effective. So what's going on in one of these deep neural networks, and why are multiple hidden layers important? What's actually happening is it's trying to do effectively more computation. It's trying to do better at disentangling and pulling apart the input, which in an original high-dimensional space is all correlated and clustered and messy. And it's trying to map it into a more understandable space as you go through. So this is kind of a way of seeing that process happening and just visualizing it. And you can kind of see qualitatively if we look at, for instance, this cluster here, which I believe is the ones. We can see it in the input space. There's a lot of like 7s that take in, which are these orange labels. Then when we go into the first layer, we notice much better separation, but there's still some of those 7s pushed into it. We go up another layer, there's like a few more there, and by the time we get to our final layer, there's virtually none of them there anymore. And you can see this separation continuing with the same 3, 4, 9, 7. You can see separation, separation, much better separation. So that's a way of understanding more of what's going on internally in these newer models. Now to move on to what are called convolutional neural networks.
Can I ask you? What did you say it was called? The visualization?
It's TSNE, which is T stochastic distributed neighbors embedding. TSNE. If you Google TSNE, that will bring it up. And it's a really cool technique, and it really helps us understand more and see what's actually going on.
Sorry, I also have a question.
Yes?
Why did the position of the clusters move?
That's an artifact of how TSNE does its computations. There's nothing actually important or native about this space. It's just learning it, and because of different random seeds and different, layers, it just ends up putting them in different spaces. It's an unfortunate thing, and it kind of makes it a little harder to compare it, but it's just a side effect of the algorithm. So, now that we've talked about kind of what deep learning does and how it's better than traditional neural networks, and most notably, we're now beating a traditional radial-based function support vector machine. That's about 88.6%, and we're up to 99%. So yay, a win for the neural networks. Now, let's talk about our final model today. So there's something that's really odd about what we've been doing this entire time. We've been taking our input and breaking it down into a one-dimensional vector. So we've been taking this native 28 by 28 image and shattering it into a 784 log vector. And as you move this 2 around or move the 7 up or down, if you actually looked at what it would look like in these one-dimensional vectors, it's incredibly difficult to see any structure in it. So we've kind of done something that's very disrespectful of our data, which is destroyed the inherent structure in it. And it kind of makes sense if we wanted to do standard matrix ops, but what if we could do something that is much more respectful of our data? So this is what convolutional neural networks do. And effectively what they do is they learn what are called kernels, which are little images that get cascaded. You could imagine instead of having that weight matrix being applied to the whole image, you're only learning like a 3 by 3 or a 5 by 5 weight matrix. And then you're cascading it across your input, and then you're learning a new representation of that input. And then you do it again. Let's say you have 4 of these kernels. They call them feature maps sometimes. You do it 4 times, so we now have a stack of 4 newly computed or transformed images. We can now do something called subsampling, which is often implemented via an operator called max pooling, which would be taking like a 2 by 2 grid and replacing it in a new representation by a single value, which would be the maximum of the values in that original grid space. Now what that's actually doing is it's kind of telling our model explicitly that you should have a form of invariance to you. So if you move your image over 1 pixel, and we're now doing this pooling operation on 2 by 2 grids, most of the time that one move over in pixel space is going to end up being mapped to the same unit. So that's a way of starting to capture some of the native invariance properties of images, which are if we flip it left or right or rotate it 90 degrees or scale it up or scale it down, it's still the same image. And we can kind of see like what's going on is that fact that scaling and rotation and translation are not native to the thing you're trying to do, which is recognize whether it's a 0, 1, or 2, is a lot of the reason for why these things get confused. And we effectively have to map from this noisy input space. And a way I like to explain that is imagine you took an image in daylight and moved that same object into nighttime. You've effectively moved from one side of your native dimension space to the other. But the thing that you're trying to recognize, the object, whatever it be, hasn't changed at all. And so that's a very difficult task to try and have a single layer handle. Lighting invariance is difficult, and as a result, we need multiple layers of computation to kind of get at handling and mapping this very complex input data into more structured and understandable spaces. So we're continuing through this chain here. We've got our 4 feature maps. Well, we can do more of those kernels. We've now made them deep, so they can correspond to, don't think this is the deep learning way. They now correspond to kernels over all our feature channels in the same way if we had like a 3D, a color image. So we'd have RGB pixel values. We can take that same thing and do it over our newly computed values. And you can think of these kind of as like little eyes scanning over the image. And the first layer eyes, if they're only like 5 by 5 pixels, about all they can do is detect, is this region bright? Is this region dark? Is there an edge here? But those are kind of the native basic, the basic types of images are edges, lightness, darkness. And if we keep doing this above, we're now learning features which respond to how those previous layers responded to the inputs. And you can kind of go higher and higher and more complicated, getting up towards, an image of a face and understanding from the corner of a mouth up to, the right side of the mouth, up to a whole mouth, up to a whole face, for instance, as you stack these things. And then finally, we have a standard fully connected guy at the end, and that maps to the standard outputs. All right, so we can do this also in Theano, and these guys are getting a little bigger now, but it's the same kind of thing. We've got our block of computation, which Theano exposes a function to us called conv2d, and that does these convolutions of these learned kernels that we're trying to learn with the input. We then do our same rectifier activation function on this, and then we do one of these max pools, which would take, for instance, a 2 by 2 area in our image space and map it down to a single value. We then add our standard dropout noise and repeat the process over and over again. So finally, when we're getting back to our normal matrix math, which would be a fully connected standard neural network hidden layer, we've got to convert this for tensor. So yeah, our native input data format has changed now. So instead of being the 60,000 by 784, we've now put it back into the native image space, which would be a 60,000. That's what this -1 operator does in a NumPy shape. Just say whatever it needs to be. A 1 by 28 by 28 image. This 1 just says, hey, we're grayscale, so we only have 1 color channel. So now we've changed our X from being a floating point matrix to a floating point tensor 4 because we work on mini batches of, and many. And now our weights look like this. There's a standard format to them, which is number of kernels, so the number of, eyes, you can think of that looking at the image for that layer, so we have 32, and they each be 3 by 3 pixels big. And 3 by 3 is a really interesting number because it's the smallest number you get in terms of a grid that actually can compute notions of like left, right, up, down, middle. And that's very important for these kinds of things. Oftentimes, traditionally, we use much larger kernels, but there's a lot of recent results saying just use more layers of smaller kernels. We get a lot of implicit regularization effects, which helps improve it. All right. So finally, because we've got this highest convolution layer, 128 filters, and a 3 by 3 grid of responses, that's just calculating that. This outputs the model as it's noisy, which we use for training. This outputs a clean one, which you don't want to add noise to your model when you're trying to actually just predict values at test time. So we've just compiled 2 versions of the model, one with noise added in explicitly and one with no noise added in. And this would be equivalent to having a dropout probability of like 0.2. So we keep 80% of our inputs on the convolution layers, and on the hidden layers we keep half. All right, so what does this actually do? Sorry I don't have better visualization, unfortunately I've run out of time at the end of this. But this can look at those like 32 responses in that first convolution layer. And then we have 64 in the second and 128 in the last. Then we have our fully connected layer. And it's kind of interesting to note what's going on here. Real quickly, there's a point which is whenever you do one of those max pool reductions, you've effectively shrunken your input space by 2. So oftentimes the heuristic we use is just doubling the number of kernels in that next layer. So we can see that as learning goes on, how these kernels or little eyes respond to the original input images kind of changes over time. And you can see, for instance, let me find some ones that are actually interpretable in here. This guy up here is, for instance, registering this very thin stroke a little bit. And then you can see these guys down here also doing similar things. Some respond to vertical inputs, which would be this spike here, for instance, on the vertical. Some respond to horizontal, which would be how this one, retifies over time over here. And then as we go up the layers, we see more selectivity. So from that first convolution feature maps, we then do the second one, and we get to see much more. Like, for instance, this one here basically says, hey, I don't care about this vertical bar here, I only care about this horizontal bar. And this guy here only cares about this center input. We can see some ones that only fire on like the corner, which would be detecting an edge on the, for instance, the hook. You can see this guy learns to fire approximately in that area. And that continues onwards and upwards. And finally, we have our 99.5% commercial accuracy. All right, that's kind of a long trip, but we've gotten to the end of it, and we now have a system that we can train using Theano to make a commercially viable system to do OCR on handwritten digits. There's another entire thing here, which is learning how to localize those digits in an input image, but assuming we already have the centered picture, we've got it. So here's a few takeaways from that very long stream of me talking. Noise is very important for regularization. It helps models explore, it helps models be robust, and it helps them prevent overfitting. Rectifiers are much faster, they're better, for faster, better learning, okay, cool. And they're kind of needed because the deeper we get, the more difficult it is for these models to learn from random initialization, and rectifiers provide a much cleaner learning signal. Also, don't use standard stochastic gradient descent. As we've seen before, it learns way slower, and these newer methods that just compute some heuristics based on the gradient are like cheaper, faster approximations of second order methods that are much better. Finally, our last takeaway, models need room to compute. If you're dealing with very complex structured data, such as text, image, and audio, it's very naive to think you can learn a model which can map from your input to your output in one step. Things are fundamentally hierarchical in images, for instance. And being able to recognize a face corresponds to a lot of subtasks, recognizing that it's a structured eyes, nose, mouth. And in order to do that, you've got to know those components. And so that's naturally a hierarchical format that makes sense to give your models explicit layers or structure. Finally, if your data has structure, your model should respect it. And for the case of images, this is done via convolutional neural networks. In the case of text, this is done via recurrent or recursive neural networks. Fortunately, I didn't get to them today. And that's kind of the message. A lot of deep learning is really just about respecting structure and some nice tweaks on standard old neural networks. Thank you.
Yeah.